So this is part 2 of our introductory lecture on quantum mechanics. The failures of the classical physics and classical atom are worth examining because I think to understand why we needed something like quantum mechanics, we have to see what problems caused us to even think in that direction. So the first is the coexistence of particles and fields. Classical particles can be described by 3 position coordinates and 3 momentum coordinates, what we call classical phase space, for a total of 3 degrees of freedom per particle. Classical fields, however, have an infinite number of degrees of freedom. If you remember from statistical mechanics last semester, we talked about the theorem of the equipartition of energy, which is a classical physics theorem, and it says that all of the energy of a system in equilibrium must be distributed equally amongst all of its degrees of freedom. And in fact, each degree of freedom provided an energy of 1/2 kT. If you remember, that was, K was Boltzmann's constant, T was the Kelvin temperature. Well, this implies that all the energy in a system would get sucked up by the fields, because they have infinite degrees of freedom, and there'd be nothing left for the particles. That's a problem. That can't be true. And of course, even last semester we stated that the classical equipartition of energy theorem doesn't work for quantum systems. And then we have the planetary model, this sort of not very realistic notion of a planetary model of the atom, where we have the nucleus is kind of like the sun, and the electrons going around the nucleus as the planets might go around the sun. And of course, instead of using gravity as the force, we use the Coulomb force between the protons and in the nucleus and the electrons. The problem with that, though, is that as the electrons orbit the nucleus, they would accelerate. And as they accelerate, of course, a moving charge emits radiation. So very quickly, they would radiate so much energy that they'd have nothing left for themselves and would topple into the nucleus, which of course doesn't happen. So that's not a really realistic view of the atom. We don't like to use the planetary model. We need something better. The other thing that was causing some concern among scientists at the turn of the 19th and 20th century was spectroscopy. Atoms emit light, but only in bursts of discrete frequencies. We call them spectral lines. Balmer was the one you might remember from modern physics. Balmer formulated the so-called Balmer formula for the visible lines of hydrogen. And it produced the right answers, but we weren't really sure why that formula worked. Moreover, it didn't work all the time and didn't explain all of the spectra that scientists were able to produce as techniques of spectroscopy got to be better and better. The other area that was not well understood, and we talked about this last semester in statistical mechanics, was that of black body radiation. Remember, we modeled the black body as a perfect absorber and perfect emitter of radiation, but it was not well understood how that method worked. And it was Planck who was the one who was able to put together, in a sense, take 2 earlier models, that of Rayleigh Jeans and the other of Wilhelm Wien, and find a way to make them fit together. As it was, Rayleigh Jeans' formula failed at short wavelengths, and Wilhelm Wien's formula failed at long wavelengths. And Planck was able to, through some mathematical finagling, find a way to make the 2 equations fit together. This was all well and good, except despite the fact that it gave the right answer, we weren't exactly sure why it worked so well. And so what he was forced to do, much against his better judgment at that point, was to invoke Boltzmann's statistical approach to the problem. And what he did was Planck assumed that the total energy of the system could be split up into a collection of indistinguishable but independent packets that we call quanta, or he called them quanta, each with an energy E, and each was distributed over a large number of distinguishable oscillators. The implication being that energy was quantized and comes in bundles equal to h times the frequency, where h is Planck's constant, 6.626 times 10 to the minus 34th joule seconds. This is a brand new idea because at that point, energy was always felt to have been a continuous quantity, not a discrete one. And it was met with great skepticism. Of course, as we know from, again, studying quantum statistics last semester, that the special case of Bose-Einstein statistics for photons, or particles of light, was the correct explanation for black body radiation, gave the right answer for black body radiation. Nonetheless, quantum statistics obviously didn't come along for another 20 years, 25 or so years. And so Planck was left to his own devices to try to explain away why we had these effects in black body radiation. Einstein accepted the reality of quanta as Planck explained it, and he used it to explain other phenomena. For example, he talked about the photoelectric effect, which entailed light shining on a metal and photoelectrons being ejected from the surface. Turns out that the electron energies were independent of the intensity of light, which defied the classical explanation, but were very much dependent upon the frequency of the incident light. Einstein's explanation said that a light quantum, or what we call a photon, incident on a surface transfers all of its energy to a single electron. And the energy of the emitted electron is equal to the energy of the photon minus whatever work function that the metal may have, as you probably learned in your modern physics lab or your advanced lab. But it's the frequency of the light that determines whether or not an electron can be removed from the metal, not the intensity. And this was, of course, confirmed by experiments. It also won the Nobel Prize for Einstein. From there, we had Niels Bohr had his own theory of the atom, where he talked about the notion that the angular momentum of the orbits was quantized. Still, this was not completely satisfying. Bohr theory only worked for one electron atoms, that is to say hydrogen or hydrogen-like atoms. It didn't predict the fine structure in the spectral lines of hydrogen, which was discovered later on, although it was observed as spectroscopy techniques got better and better. And it really couldn't explain why atoms would bind to form molecules. So there are a lot of things that were not terribly satisfying about what we had at the time. Another effect that sort of demonstrated the particle or corpuscular nature of light was the Compton effect. You probably studied this in modern physics. Compton designed an experiment to allow particles of light to collide with electrons. He predicted that the frequency of the light quanta would change as a result of the interaction, and results showed that light quanta have to have momentum, as though they were a small projectile. So at this point, we have this duality of light as both a particle and a wave, and it just depended upon which experiment you performed. In some experiments, light behaved like a particle. In other experiments, light behaved like a wave. in 1905, Einstein published his theory of the special theory of relativity, which deserves a great study in its own right, but we won't do that here. But suffice it to say, there's one expression from the special theory that we want to continue to look at, and that is the energy expression. E squared is equal to p squared c squared, momentum squared times the speed of light squared, plus m squared c to the fourth, which is the square of the rest energy of the particle. Particles with zero mass, like photons, would of course have, this term would be zero, and so for those particles, the energy would just be P times C. Furthermore, de Broglie came along and talked about relating the special theory of relativity results with Planck's quantum theory. In other words, he talked about the energy being equal to h times the frequency and also equal to the momentum times the speed of light, which gave an equation where we would assign to each particle a wavelength, lambda equal to h over f, h over p, I'm sorry. What this says is that any moving particle that has a momentum should have a wavelength associated with it. And of course, we saw that later on this would happen in experiments by Davison and Germer that showed that a beam of electrons had wave-like properties. So those were the kinds of things that led up to the notion of we need a better explanation of nature. Because waves were so intimately involved in nature, one might have the idea in the early 1900s that there ought to be some wave equation to describe this behavior. And while we're not exactly sure what led to the proper equation for non-relativistic quantum mechanics, what we can do is advance a plausibility argument as to how the Schrodinger equation could have been arrived at. Now, I say this with a great warning, which is the following. If you look at page 1 in Griffith's text, you'll see that the Schrodinger equation is written right on the first page. His point being that it can't be derived. And that's correct. We don't know a way of deriving the Schrodinger equation, which is the fundamental equation in non-relativistic quantum mechanics. But we can advance a plausibility argument based on the discoveries that were made in the early 1900s and make it at least plausible as to why not only would Schrodinger believe that there was a wave equation that should result from this, or a type of wave equation, but that he could figure out what the equation should be. So, suppose we were to make this plausibility argument. First of all, it has to be consistent with the ideas of both Einstein and de Broglie. So, I should be able to write a wavelength as h over p, and an energy as h times the frequency. It has to be consistent with the total energy equation, what we call the Hamiltonian, p squared over 2m plus potential energy. Just total energy is equal to kinetic energy plus potential energy. Thirdly, it must be linear. So if psi of x and t is my wave function, it has to be such that if psi 1 of x and t is a solution, and psi 2 of x and t is a solution, it must be that the sum of psi 1 and psi 2 are also solutions to the wave equation. And any linear combination thereof. So if I were to write it as C1 psi 1 times plus C2 times psi 2, that should also be a solution. That is one of the criteria of linearity. The other thing about this is, if I can do this, I can make more plausible that I'll see the results of Davison and Germer, which is to say you'll see interference between, let's say, electrons or other particles. Or my potential should be a function of x and t, but for now we can be well served by having the potential be time independent. So we'll just make it dependent upon space and not upon time. And let's make it even easier. We'll just call it a constant for now. We're not going to lose any generality by doing that. We'll call this the free particle case, since for a free particle, force is 0, so minus dv dx would be 0 in that case. We'll also say that momentum is a constant of motion, and energy will be constant as well. So we can rewrite our energy equation, equation number 2, using the expressions in number 1, to say h squared over 2m lambda squared plus v is equal to h times f. I'm going to make the substitution. I'm going to use h bar as equal to h over 2 pi. That's a very familiar notation that we use in physics. Lambda, I'm going to write as 2 pi over k, and I'm going to write omega as 2 pi times the frequency. K is, of course, the wave number. And I'm going to use, instead of lambdas and f's, I'm going to use k's and omegas. And my energy equation looks like this: h bar squared k squared over 2m plus v is equal to h bar omega. Now, to satisfy linearity, every term in our new differential equation has to be linear in psi of x and t, which means it's got to be proportional to psi of x and t to the first power. Let's try some trial solutions, okay? Let's try something like this. Suppose we try psi of x and t is equal to sine kx minus omega t. That's an example of a traveling wave. Could it possibly suffice under these conditions? Well, the problem is, if I look at my energy equation, that may not be so good. Because notice, in the energy equation, I need to have terms like k squared and omega coming out of the wave equation, coming out of my wave function. If that's the case, I know I can get an omega if I take one time derivative, and I can get k squared if I take two space derivatives. But that's different than the type of wave equation that we're familiar with. Typical wave equations are both second order in time and in space, not first order in time and second order in space. Nonetheless, in order to make this work, we're going to need an equation that's linear that's first order in time and second order in space. Let's put in a trial differential equation. So alpha d squared d psi of x and t squared plus v of x t psi of x and t is equal to beta times d psi of x and t dt. So where I need to determine alpha and beta. No, it's first order, I should say it's linear in psi, which it has to be. It's first order in time and second order in space. Well, let's see if it works. First, let's make it easier. Let's set v equal to v naught. We'll make it a constant. And we'll use psi of x and t as sine kx minus omega t, a traveling wave moving to the right or moving in the positive x direction. So if I operate on psi with this expression, what do I get? I get minus alpha k squared sine kx minus omega t plus v naught sine kx minus omega t is equal to minus beta omega cosine kx minus omega t. We're in trouble already. This is going to be a problem. Because what's going to happen is there's no way this can work unless sine kx minus omega t equals cosine kx minus omega t. No other time. Got to try again. Let's try a combination of sines and cosines. Let's try something like psi of x and t equals, we'll do it this way, cosine kx minus omega t plus gamma sine kx minus omega t, where gamma is some constant. Notice what happens. Take the first derivative, I get d psi dx is minus k sine kx minus omega t plus k gamma cosine kx minus omega t. Second derivative of psi with respect to x is equal to minus k squared cosine kx minus omega t plus minus k squared gamma sine kx minus omega t. My first derivative of psi with respect to t turns out to be omega sine kx minus omega t minus omega gamma cosine kx minus omega t. If I plug these last two expressions into my proposed differential equation, what I'm going to get will be 3 equations and 3 unknowns. That being the case, if I solve them simultaneously, alpha, beta, and gamma turn out to be gamma is plus or minus square root of 1, or we use the plus I. Alpha turns out to be minus h bar squared over 2m. And beta turns out to be plus or minus IH bar. By convention, we typically choose, this could be plus or minus I, but we tend to choose plus I for gamma, and we tend to use plus IH bar for beta. If I put that all together, my equation looks like minus h bar squared over 2m d squared psi dx squared, that's a t, plus v naught psi x t equals I h bar d psi dt, x and t. This is what we call the Schrodinger equation. For a free particle. Now at this point we can only postulate that this equation is going to work regardless of what v we put into it. Nonetheless, this is, as it turns out, the equation that works in quantum mechanics, at least non-relativistic quantum mechanics. It's called the Schrodinger equation. I'm not sure if that's exactly the thinking that he used to come up with this equation, but as I say, it's a nice plausibility argument, and I find it at least a little bit more satisfying than just starting page 1 with the Schrodinger equation. We're going to use this equation for almost the entire course. But that's not all. We're going to arrive at the Schrodinger equation from a completely different means, and that is using a linear algebra approach. And that's going to be the topic of our next lecture.